Okay, welcome back to the session of the differential equation. In the last class we discussed about the separable equation. Today we like to discuss about first order linear ordinary differential equation. The general form of the first order linear ordinary differential equation is y dash plus p of x into y is equal to g of x. Here p of x and g of x are the functions of x alone, where x is the independent variable. Now we have two methods to solve this first order linear ordinary differential equation. First one is method by finding integrating factor. Second one is method of the variation of the parameter. First one is method to finding integrating factor. Second one is method of variation of the parameter. Method of the variation of the parameter. Here firstly we concentrate on method to find the solution by integrating factor. See, generally we have I am denoting this equation as equation number 1, y dash plus p of x into y is equal to g of x, where y dash stands for dy by dx, y dash stands for dy by dx. See, we have to find out integrating factor as a function in x. I am denoting that as a b of x, and I like to multiply this equation 1 with mu of x. Therefore, this equation 1 becomes it changes as mu of x into dy by dx y dash plus p of x into y into mu of x is equal to g of x into mu of x, is equal to g of x into mu of x. See, I am denoting this as equation number 2. Consider d by dx of mu of x into y. This is, I can treat this as this is first function and this one y as a second function. We are using here for differentiating the product rule, first function into derivative of the second and second function into derivative of the first. Therefore, this is equal to first function mu of x into derivative of the second function, that is derivative of y, that is y dash, plus second function y into derivative of mu of x, that is equal to mu dash of x. And I am putting this as equation number 3. See, mu of x into y dash plus y into mu dash of x. The left side of equation 2, we are treating as derivative of mu of x into 2. Left side is we are treating as derivative of mu of x into y, that is the right side of equation number 3. So, by comparing these two, the first function is mu of x into y dash, here the first term is mu of x into y dash, here the second term is y into mu dash of x, here the second term is p of x into y into mu of x. So, from 2 and 3, from equations 2 and 3, we will get p of x into mu of x into y is equal to y into mu dash of x, y into mu dash of x. From the last relation, we will have p of x into mu of x is equal to mu dash of x. P of x into mu of x is equal to mu dash of x. We can write mu dash of x as d mu of x divided by dx, and this is equal to, here left side is same, p of x into mu of x. So, we can take as we done in previously variable separable, I would like to take this dx to be here this is to be here and dx to be here and mu x to be here. Therefore, we can write this as d mu of x divided by mu of x is equal to p of x into dx, p of x into dx, integrating both sides, When we integrate this on both sides, we will have integral of d mu of x divided by mu of x is equal to integral of p of x into dx, and we will get this is d mu of x divided by mu of x. What about the answer? This is the logarithm of denominator is mu of x, numerator is derivative of numerator, therefore, that is equal to log of mu of x, and this is equal to integral of p of x dx plus c. And here we need to find out the integrating factor. Mu of x is the integrating factor. So, we have to remove this logarithm. To remove, we apply the exponential function, on both sides. What will happen? E raised to logarithm of mu of x is equal to e raised to integral of p of x dx plus c. So, e raised to, we know that the formula e raised to log of e raised to x is equal to x, as well as e raised to log x is also is equal to x. From this, e raised to log of mu of x, instead of x here we have mu of x is there. Therefore, e and log will go on, the mu of x only it will remains here, mu of x is equal to e raised to integral of p of x dx plus c. For the convenience, without loss of generality, we are taking c is equal to 0. C is arbitrary constant, in particular we can treat c as a 0 also. When we taking c is equal to 0, what will happen is that mu of x is equal to e raised to integral of p of x dx. This is actually the integrating factor of the first order ordinary linear differential equation. And by using this integrating factor, we can easily find the solution of the first order ordinary linear differential equation. We have y dash plus p of x into y is equal to g of x is the first order ordinary linear differential equation. The solution of this ordinary differential equation is the function y. Y is actually the solution of the differential equation, because this is the dependent variable, it will exist with the help of the independent variable x, and this y into the integrating factor mu of x is equal to integral of mu of x, the integrating factor, into the non-homogeneous part of this first order ordinary linear differential equation, that is g of x dx plus c. By using this formula, we can solve the first order linear ordinary differential equation. See here, this is a part of the method of finding integrating factor, and this mu of x is called the integrating factor, and our formula is that to solve this one, y dash plus p of x into y into g plus is equal to g of x. That is, y is the solution of the ordinary differential equation and mu of x is our integrating factor. This is equal to integral of mu of x into g of x dx plus g. See, our solution is y is equal to, simply we can write this as we have taken this mu of x to be here, and this is equal to 1 by mu of x into integral of mu of x into g of x dx plus c. The c is the constant of integration and that is what is the arbitrary constant, and as we done in every solution of the first order ordinary linear differential equation, we have, if we have initial value problem, what is actually initial value problem? Y dash is equal to f of x y is the general form of the first order differential equation if it involves y of x naught equal to y naught, then this problem is called initial value problem. And the initial value problem is actually a ordinary differential equation. There is one condition, the initial condition will be given there, and there is this point x naught is the initial point and y naught is the value of the y on that initial point. By replacing this x naught and y naught, we can find this arbitrary constant c. There exists, as because of it is an arbitrary constant, it will be treating as a variable. As like a variable, it can have a opportunity to take any value as its own wish, but while giving the initial condition, there is the opportunity will loses. There have only one possibility to take the solution. That solution is called the particular solution. The only single solution, that is what is called the particular solution. So, as like every ordinary differential equation, we can say that this first order ordinary differential equation have a general solution. This solution is called general solution. The general solution can find by using this formula, as well as if that or even that ordinary differential equation is a initial value problem, one thing is that it should have a particular values are given there, that is the function value y at a point x naught is given here. That is why only one single solution will exist there, that solution is called a particular solution. And see, we can move to some of the examples of solving first order ordinary linear differential equation, and by using the method of integrating factor. It is one thing is that we have to just bother about only the integrating factor. This integrating factor is mu of x, and this mu of x by finding e raised to integral of p of x dx, where p of x is the coefficient function. See, our equation is y dash plus p of x into y is equal to g of x. See, this is the coefficient function of y. So, by using that function value, simply we can find out the integrating factor. We can move to the first example, the example 1. We can move to the first example, example 1. dy by dx minus y is equal to e raised to 2x. See how we will solve this differential equation. Before going to solve this differential equation, firstly we have to check whether is it method of variable separable or first order linear differential equation or any other some other forms. First of all, we have to identify the form of the differential equation. Here simply we can compare with this one. This is y dash dy by dx is here, and some p of x into y is here, that is minus y is here, and after the equal to sign there is a function, that is what is e raised to 2x is there. By comparing this general form, we can identify p of x. P of x is equal to minus 1, and g of x, we have the value of g of x is here, that is e raised to 2x, e raised to 2x is here. And from here the because of value of p of x, we can find out the integrating factor. So, finding the integrating factor, the integrating factor mu of x is equal to, by the formula we have e raised to integral of p of x dx. We have the value of p of x is here minus 1. We will apply the value minus 1 to be here. So, we have e raised to integral of minus 1 dx, that is equal to e raised to minus x. So, integrating factor is equal to e raised to minus x. Now, we can move to our formula. What is our formula? Is that the solution, we can find the solution, can find general solution, by using the formula y into integrating factor is equal to integral of integrating factor into g of x dx plus c. So, y into the integrating factor, here we found the integrating factor as e raised to minus x. So, y into e raised to minus x is equal to integral of integrating factor. The integrating factor is e raised to minus x into g of x. What about g of x? Here we found the g of x is here, we will apply here g of x is equal to e raised to 2x dx plus c. So, y into e raised to minus x is equal to integral of, see, e raised to minus x and e raised to 2x, e raised to 2x plus minus x, that is equal to e raised to x dx plus c. So, this is equal to y e raised to minus x is equal to integral of e raised to x. Integral of e raised to x is again e raised to x, that is e raised to x plus c. We have to find the solution. We know the solution is the y itself. We are removing this integrating factor e raised to minus x from the left side. We are taking that is to be right side. Therefore, y is equal to 1 by e raised to minus x into e raised to x plus c, into e raised to x plus c. See, this is y is equal to, I am multiplying this is to be here, that is e raised to x divided by e raised to minus x plus c divided by e raised to minus x. We can take this e raised to minus x to be numerator. Therefore, e raised to minus x will be e raised to plus x. So, e raised to x plus x, again we will get e raised to x plus x as y is equal to e raised to x plus x e raised to 2x and plus c, e raised to minus x we have taken to be numerator. Therefore, e raised to minus x is equal to e raised to plus x. So, now we arrived our solution. Our solution is y is equal to e raised to 2x plus c into e raised to minus x. In our question, we did not mention the initial condition, that is why we are unable to be find out the particular solution. This is the general solution. This is the general solution of our given differential equation. And the given differential equation is ordinary linear differential equation. See, there are many applications for this linear ordinary differential equation. In many fields, applied fields, we are using this ordinary linear differential equation, and we can move to the next example. Example 2, solve sin 2x dy by dx is equal to y plus tan x, is equal to y plus tan x. Listen, we can compare this is to our general form. Which is our general form? General form is y dash plus p of x into y is equal to g of x. By comparing this one with y dash, there is no other function is coming, but here dy by dx is coming with a sin 2x. So, this is the additional one. We have to remove this is from here. Now, this form, this is now by seeing this one, this is not a linear, this is not a linear. So, we have to make this equation as a linear differential equation. For that I am putting this as a equation number 1, and we are dividing 1 with a sin 2x, dividing 1 with a sin 2x. What will happen is that we are dividing this with sin 2x. So, this part is sin 2x divided by sin 2x will be 1, therefore, dy by dx is here, here it is equal to y divided by sin 2x plus tan x divided by sin 2x, tan x divided by sin 2x. I am taking this part is to be here. So, we can write this as a dy by dx, while taking that to be here, minus 1 by sin 2x into y is equal to tan x divided by sin 2x, sorry, sin 2x. See, compare these two. Dy by dx is here, y dash is here, and as well as there is a term of y is there and the function in x is there, minus 1 by sin 2x is that function. This is actually the p of x. And see, g of x is here, we have g of x is a function in x, tan x by sin 2x is a g of x. So, we can write this, I am putting this equation as a equation number 2. So, from equation number 2, we can write this p of x is a function that is minus 1 by sin 2x is equal to minus 1 by sin 2x, and we can write this, we can find this is g of x is equal to tan x divided by sin 2x, tan x divided by sin 2x. See, we have to find out the integrating factor. We have the formula, the integrating factor is equal to, the integrating factor is equal to e raised to integral of p of x dx. We apply the value of p of x to be here. Therefore, this is equal to e raised to integral of minus 1 by sin 2x dx, minus 1 by sin 2x dx. See how we will solve this one is here. Sin 2x is here, this is equal to e raised to integral of minus integral of 1 by sin 2x dx is there, minus 1 by sin 2x dx is there. So, we can write this as a, this is equal to e raised to minus integral of, we have the formula sin 2x, we have a formula for sin 2x is there, formula for sin 2x is equal to sin 2x is equal to 2 sin x cos x, sin 2x equal to 2 sin x cos x. So, we can replace this sin 2x by this formula. Therefore, this is equal to 1 divided by 2 sin x cos x, 2 sin x cos x dx. See how we will integrate this is. Here we are unable to be find out the actual, we have to apply substitution method also, we need, if the denominator is a function whose derivative is numerator, then we can use the substitution method, but we are unable to apply even substitution method is also here. That is why we have to convert this is to be how can this is to be making this function to be a substitution method function. That is why we can rewrite this as a e raised to minus 1 by 2, I am taking minus 1 by 2 is outside, and this is equal to 1 pi sin x is here, sin x is here, and I am dividing this sin x by a cos x. So, I divide this cos x, simply I divide the cos x. To compensate that cos x, I have to multiply one more cos x to this numerator, that is cos x into cos x, that is the cos square x dx, that is the cos square x dx. See, we can change this function as like this. See, e raised to minus 1 by 2 integral of I am taking cos square x to numerator, 1 by cos square x is 1 by cos square x is the sec square x, 1 by cos square x is sec square x, and we have the formula sin x by cos x. Sin from the very early standards we studied it is that sin x by cos x is tan x dx. See here you can see that the denominator is tan x, numerator is sec square x. See the derivative of tan x is sec square x. That is why we can use the substitution method. That is why we can use the substitution method. So, put u is equal to tan x. Put u is equal to tan x. That is why du is equal to derivative of u, derivative of tan x. Derivative of tan x is sec square x into dx. So, by applying this to be here, this is equal to e raised to minus 1 by 2 integral of du is equal to sec square x into dx. This sec square x into dx is equal to du, and the tan x is equal to u, du divided by u. Now, this is okay, e raised to minus 1 by 2 integral of du by u, integral of dx by x is equal to log x, integral of du by du is equal to log q, log q. Therefore, this is equal to e raised to minus 1 by 2. We can replace log q, instead of u we can replace by tan x. So, e raised to minus 1 by 2, e raised to minus 1 by 2 log of, instead of u we replace by tan x, log tan x. See, again we can write this as, again we can write this as e raised to log tan x, log tan x whole raised to 1 by 2. It will remove e and log is there. Therefore, this is equal to whole raised to minus 1 by 2 is here, log tan x. Therefore, tan x whole raised to minus 1 by 2. Therefore, this is equal to 1 by square root of tan x. So, this is our integrating factor. This is our integrating factor. Now, we found our integrating factor. By the formula we know that we can find the solution y into integrating factor is equal to integral of integrating factor into g of x dx plus c. See, integrating factor is here. Therefore, integrating factor y into integrating factor 1 by root tan x is equal to integral of 1 by root tan x into g of x. What about g of x? We know that we have taken g of x is equal to, we have taken g of x is equal to tan x divided by sin 2x, tan x divided by sin 2x. This is equal to tan x, we can rewrite tan x as sin x divided by cos x, and we have the formula for sin 2x is equal to 2 sin x cos x. Therefore, we can cancel sin x and sin x, we can cancel. This cos x is the denominator, this is the numerator of the denominator. Therefore, both will merges. Therefore, 1 by 2 into 1 by cos square x is there. Therefore, this is equal to 1 by 2 into cos square x, we can write as 1 by cos square x as a sec square x is there. So, we have instead of g of x, we have integrating factor into 1 by root of tan x is there, and we have to replace instead of g of x by 1 by 2 sec square x dx plus c, 1 by 2 sec square x plus c. See, inside this integral we have taken 1 by 2, we can take the 1 by 2 is outside. I am raising these things. See, this is equal to 1 by 2 into integral of 1 by root tan x into sec square x dx. Therefore, sec square x divided by tan x root tan x dx plus c. See, as we discussed earlier, tan x, the derivative of tan x is sec square x. So, we can use substitution is here. Therefore, we can put u is equal to, we can write this, put u is equal to tan x, du is equal to, as we did in earlier, this is equal to sec square x dx. So, this will be equal to 1 by 2 into integral of sec square x dx is here, and sec square x dx is du. So, sec square x dx is equal to du divided by root of tan x, that is equal to root u plus c is there. So, this is equal to 1 by 2 into integral of u raised to minus 1 by 2 plus c. We have integral of x raised to n dx is equal to x raised to n plus 1 divided by n plus 1 plus c. Therefore, this is equal to 1 by 2 into u raised to minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1 plus c is there. This is equal to 1 by 2 into u raised to minus 1 by 2 plus 1 is 1 by 2 divided by minus 1 by 2 plus 1 is 1 by 2 plus c is there. Therefore, we can cancel 1 by 2 and 1 by 2. See, the remaining things are, this is equal to y into 1 by square root of tan x, square root of tan x is equal to, we found here it is equal to u raised to 1 by 2 plus c. See, we applied u as a tan x, we can replace instead of u by tan x. Therefore, this is equal to, therefore, this is equal to y into 1 by root tan x is equal to root of tan x whole raised to 1 by 2, that is equal to root of tan x plus c. And we can again we can rewrite one more time. I am taking this tan x to be here, both we have to multiply with root tan x. Therefore, y is equal to root of tan x into root of tan x is equal to tan x plus c into square root of tan x, c into square root of tan x. And now, our task is over. This is the general solution of given ordinary differential equation, which is the linear ordinary differential equation. And as well as here c is also arbitrary, because in our question there is not mentioned about the initial condition. If they mentioned initial condition, as I said earlier, there is a possibility for a particular solution instead of a general solution. We have many linear differential equation are discussed in our literature. You can go to the Google and you can find out many examples of differential equation. In our classrooms, we are discussing only some minor examples of this differential equation to understand the concepts. You can go to Google also, you can find out many applications of the differential equation. Keep watching on these videos. Well, I will come to again with some of the problems of the ordinary linear differential equation. Thank you very much.